Good morning, chemists. Let's get started. So we're going to continue on with chapter 15 today, but on Tuesday next week, since it's right before your midterm, we're going to just devote Tuesday's lecture just for midterm 1 review. I don't know if I'll prepare something or maybe I'll go through the recitation packet. I don't know. And then later that night on Tuesday, I will do that Zoom session. The activity packet's already posted there. All right, we posted the Respondus Lockdown Browser test quiz. So I have it linked in a couple places. I think Jennifer sent out a email to remind you what you need to prepare and what you need to bring for the midterm exam next week, and it's linked there as well. So please, please, please test your Respondus Lockdown Browser. Don't assume that it works from last year, just test it. My trick is if you see a gray banner at the top of your screen when you go to take the quiz, you're inside Lockdown Browser. But if it's a colored banner, then you're in Canvas and you got to try again. And then you have to duo again. So while I'll be at your exam and I usually walk around, and if I see colored banners, I'm like, you're not in Lockdown Browser. You'll try to put in the password and it won't work. So do make sure you see that gray banner, excuse me, at the top, and to ensure that you are inside a Lockdown Browser. All right. Okay, so on Tuesday, we started chapter 15 here, where we're talking about big K, chemical equilibrium. So the first half of the chapter, we kind of just talked about the details of what this big K is. Chapter 14, we talked about small k, little k, which is rate constant, related to our rate laws. But big K describes chemical equilibrium. Equilibrium meaning we have this double arrow. So we're finally going into detail about that double arrow. We'll talk about this double arrow for the next 3 chapters. So big K is related to the relative concentrations of products and reactants at equilibrium. When your system is at equilibrium, we don't see a net change in concentrations of products and reactants changing with time, but instead we have a dynamic equilibrium where the forward and reverse reaction rates are equal to one another. So that is essentially the analogy for chemical equilibrium. And so what we see is the relative ratios of products over reactants is the magnitude of K. So big Ks, if we have large equilibrium constants, typically what species is mostly present at equilibrium? Large values of K? Mostly products, versus small Ks are typically have reactants at largely present at equilibrium. So with that in mind, I'm introducing a new type of table that we're going to be using extensively for the next 3 chapters, ICE tables. So ICE stands for initial, change, and equilibrium. This is different than a BCA table. Though it's constructed similarly, we just use it differently. BCA tables we used to determine limiting reactants when we studied reactions that had just single irreversible arrows. So irreversible reactions, we used a BCA table. But with chemical equilibrium, we use ICE tables, with those double arrows. But they are constructed basically the same, where the change line is dictated by stoichiometry. So we did an example here. This has no solution to it. I give you a chemical reaction. It's all aqueous. If we start with A and B, our reactants, our reaction only has one direction to go, in the forward direction. So we use stoichiometry to describe the change line. I don't know how much it's going to change, so I'm just going to say, okay, if I lose an X amount of A, I also have to lose a 2X amount of B. So again, dictated by stoichiometry. But at the same time, I gain a 2X amount of D and a 3X amount of E. And so then you add up your columns, and the big idea with ICE tables is that the equilibrium line is what goes into your K, your equilibrium constant expression. So then we got this like crazy looking expression here. This has no solution to it, but you could in fact solve it if I gave you a K value, an actual K value. And then you can solve for x. X is not our answer here. We would have to insert x into the equilibrium line, and that should tell me the relative concentrations of species at equilibrium. We will have less A and B than what we started with, but then we'll have a little bit more products there. So that's how we construct an ice table. We need to use it. We're using our calculators today, so might as well just pull those out, your calculators. I like to organize things and come up with strategies and share them with you guys. And so ice tables can be difficult, all right? But I'm trying to give you guys a strategy that's as simple as possible. Essentially, when given a chemical equilibrium and we have to construct an ice table, there are two kinds of questions that we can ask you. The first kind here, which I call question type 1, is you're given initial concentrations and a final concentration, and you need to calculate K, the rate, chemical, equilibrium constant. I call this the Sudoku method, and I'll show you why. So let's look at this question. So we got a bunch of examples that we're going to work through. So we have a closed system containing only hydrogen and iodine gases at this temperature, and it reaches equilibrium. All right, and then at equilibrium, we measure that the concentration of HI, that gas, is 1.87 molarity. Calculate K, Kc for this reaction. Because everything's given in molarities, great, we don't have to do any conversions. We can just plug in molarities straight into our ice table. So I give you the chemical reaction, so let's construct our ice table. We need to put in the given information in the right places, all right? So just going through the sentences here, the closed system contains only hydrogen and iodine, 2 molar iodine at this temperature. So we're not using the temperature here. That temperature is just relating to the K value that's measured that we're going to calculate here. So in what line should I put these two concentrations? Initial, yes, those are the initial conditions, and then something's going to change in order for the reaction to reach equilibrium. So the important thing here in ice tables, we can just straight put in molarities because the volume is not changing during this chemical reaction. We can just use molarities. We could also use pressures if this question was given in pressures as well. That's different than BCA tables, because when we used BCA tables, what was the unit? What did the unit have to be? Moles, yes. But we don't have to be in moles. We could put this in moles, but we don't have to. We can leave it in molarity. All right, so that's 1 molarity. Iodine is 2 molarity. And then how much HI do I have initially? 0, yes, yes. So that is implied. That is implied because I'm saying you only have the reactants present. And so at this point, just do the regular ice table stuff. So if we look at this chemical reaction, what direction does this have to go? It has to go forward. So under the change line for hydrogen, what am I going to put? Minus X, right? I'm saying minus X because I don't know how much it's going to change, so I'm just going to call it X for now. All right, so minus X of hydrogen, then how much do I lose of iodine? Also X, but then how much do I get of HI? 2X, but it's plus 2X, because we're gaining it. All right, and then you add up your columns. So at equilibrium, we will have, I'm going to just drop the sig figs in the units, 1 minus X of hydrogen, 1 minus X, oh nope, not 1, 2 minus X of iodine, and then, what is it? Oh, then just 2X amount of HI. All right, and so remember, the big idea with K, chemical equilibrium, is that the equilibrium line in our ice table is what goes into our K expression. So the next step is to build our K expression. So let's write what that would be. So Kc for this chemical reaction, products over reactants. So it's going to be concentration of HI over, squared, sorry. It's squared because of that coefficient of 2, over concentration of H2 over concentration of I2. Great. So we need to figure out what those equilibrium concentrations are for that Kc expression, and then we can calculate K. So how do we do that? We're going to play Sudoku. So let's look at the last piece of information that's given here. All right, so we use the initial concentrations, but it says at equilibrium, HI equals 1.87 molarity. So this piece of information gives us what X is. So do you see that this concentration is equal to that expression? Because we already determined at equilibrium 2x equals the HI concentration. So I know that 2x equals 1.87. So now do we know what X is? Yes, now we do know what X is. So X equals half of that, so 0.935, thank you. All right, is that my answer? No, it's not my answer, but it is the answer of what X is. And so now we need to just plug in X to the rest of the equilibrium line so we know the concentrations of everything else at equilibrium. So that is X, so that means that H2 is equal to 1 minus that number, so 0.935. So the concentration of H2 at equilibrium is equal to 0.065 molarity. The concentration of I2 at equilibrium, so we'll just do 2 minus that X that we just calculated, 0.935, sorry for my messy work, is equal to 1.065 molarity. And then, I mean, you don't have to plug that X back into 2X because we are given the concentration of HI at equilibrium already. So this is what I call the Sudoku method, where you just have to, build the table and then kind of work your way back in to fill in the rest of it. All right, so these are the numbers that we're going to plug into our Kc expression, not that one. So there's HI, there's H2, and there's I2. And those are the numbers we plug in. So now it's just plug and chug. 1.87 molarity squared over H2, which is 0.065, and then 1.065. All right, and then we get a Kc of 50.5, or 51. Maybe 51 because H2 only has 2 sig figs. Whoops, 51. I'm going to say 51. Okay. So that's how we use an ICE table, and this is what I call question type 1, where we're given different pieces of the ICE table and we got to fill it back in. All right. The whole idea here is that they gave us an equilibrium concentration, just one of them, but that's enough for us to fill in the rest of the table. All right. How do we feel about that one? Good? Okay. Are we going to do another one, type 1? Yes, we'll do another type 1. Okay, again, it's another Sudoku method. So let's look at this example. We have a mixture of this, and that, and we place it in a 1-liter vessel at 300 Kelvin. Again, I have to just say the temperature because this K, big K, is related to that temperature. And then I tell you, at equilibrium, NO concentration equals that. Let's calculate Kc again. So let's, I'm just going to get the equilibrium expression so I know what I'm aiming for here. Remember, just products over reactants. So I need to figure out what is the equilibrium concentration of N2. I need to figure out the equilibrium concentration of H2O squared over the concentration of NO squared over the concentration of H2. Squared. And again, these are all at equilibrium because you might really want to just put these mole amounts into the Kc expression, but these mole amounts, so 0.1 mole of NO, 0.05 mole of H2, those are initial concentrations, so we cannot put that into our K expression, but we can put it into our ICE table. So let's make that ICE table. All right, so I said previously, we want to we can put molarity concentrations into the ICE table. So let's do that instead of mole amounts here. Because this question says everything is in a 1-liter container, these mole amounts are also molarity amounts. So I'm just going to convert straight to molarity because I have to use molarities in this Kc expression because C means concentration. We want to use molarities. So initially, there's 1.10 molarity of NO. There's 0.05 molarity of H2. And then there's 0.10 molarity of water. How much nitrogen is there initially? 0, yes, that is, again, implied. It's implied because I didn't give you amount, that I'm saying there's only these 3 things in the container. Okay. Can we predict which direction this reaction will go? It has to go forward. Well, I know that. How do you know that? There's some water on the product side. Can it go in reverse? There's no nitrogen. Yeah, so since there's no nitrogen, the reverse reaction cannot happen. You need both components in order to go in the reverse reaction. So this reaction has to go in the forward direction. So I can fill in my change line, minus 2x, plus x, and then plus 2x. So this one's a little bit more complicated than the previous one, but the strategy is still the same. So we add up our columns to get our equilibrium lines. So equilibrium concentration of NO is 0.1 minus 2x. Hydrogen is 0.05 minus 2x. Nitrogen is x, and water is 0.1 plus 2x. I like to put them in parentheses so you can see, okay, each term, that's the concentration at each term. Okay. See where we're going? This is the same question as the previous one. So we use the last bit of information here where I tell you the concentration at equilibrium for NO gas is 0.062 molarity. So that tells me which piece of information. That tells me what this whole expression equals. So 0.1 minus 2x equals 0.062. That's what was given in the question. All right, and then that allows us to calculate what x is. So x in this case is equal to 0.019 molarity. And so that's the term we'll use to plug into the rest of the equilibrium line to figure out what are the equilibrium concentrations of everything else. And so when you plug that value into the rest of the equilibrium line, you see that at equilibrium, hydrogen is equal to something like 0.012. Okay, so that's hydrogen. Nitrogen is just X, so it's 0.019. So that's nitrogen gas. And then you do the expression for water, and you see we gained a little bit, so 0.138. Sorry, I'm ignoring sig figs. I'm doing a lot of writing right now. So H2O, there we go. So those are all of the concentrations I need for my K expression. Sudoku method. All right, and so we plug those into our K expression. So let's do that. All right, so our Kc is equal to, so just be really careful of where you place things. So nitrogen is 0.019. Water is 0.138, and we're going to square that. NO gas is, they gave it to us, so it's 0.062 squared, and then hydrogen gas is 0.012 squared. All right, and then, then just plug and chug, and you'll see that Kc for this specific reaction is 654. Good. Am I going too fast? Is this okay? All right. Well, this is our second one. And so it's the same exact process. So fill in your ice table, put the things in the appropriate place, subtract or add your change line following stoichiometry, get your equilibrium expressions for each of the substances. Typically, we have to give you a piece of the table for you to calculate Kc. All right. Good. So another way we could ask this question, so what you see here is like I could give you initial concentrations. I could give you an equilibrium concentration. or I could give you Kc. So there's kind of like 3 different variables here with this Sudoku method. And so another way I could ask this question is I could give you equilibrium concentrations, and I could give you Kc, and you could back calculate to the initial line. And so it's the same kind of process there. And we'll do some examples, more examples like that in chapter 16. Okay, so I would say this question type is the easier one, What's harder, all right, because I told you there's 3 kind of variables here: initial, equilibrium concentrations, and Kc. The second type of question is where I give you Kc, I give you the initial concentrations, and we calculate the equilibrium line. All right, this oftentimes requires the quadratic formula, but that is not what I'm doing right now. Nope. Okay, I have to do a couple slides, and then we will talk about method question type number 2. All right, so in the previous questions, we easily predicted which direction the reaction will go, basically using our intuition. In the first example, we only had reactants, so the reaction, the equilibrium must proceed in the forward direction. So we knew which way to put the minus and plus x. We already knew that using our intuition. In the second one, we had this missing piece of nitrogen. So that means the reverse reaction could not happen. So again, the forward reaction has to happen. We knew the direction the equilibrium had to go. Well, sometimes it's less obvious what direction the chemical equilibrium will go. So what we do when we're given a situation, if we're given, non-equilibrium concentrations, we have reactants and products, it's not as obvious which direction it goes. We can do a back of the envelope type calculation to predict the direction it needs to go. Again, if you keep in your back pocket and know that K is equal to products over reactants, it'll help you predict the direction. So how we predict the direction when given non-equilibrium concentrations is we calculate what's called Q, the reaction quotient. Essentially, you just put the non-equilibrium concentrations into the K expression and calculate what it is. And what we do is we compare that value that we calculate, the Q. So the reason it's Q and not K is because it's not equilibrium conditions. If we compare the Q to the K value for that specific reaction, we can predict which direction the reaction must go to achieve equilibrium. So, because the idea here is, okay, what if, in the previous reaction, you calculate Q and you get a number like 5, right? Okay, so just whatever concentration is given initially and you calculate 5. But you're also given that K is equal to 0.1. So if we look at this number, 0.1, K is 0.1, what is mostly present at equilibrium? Products or reactants? Reactants. Okay, but what if we look at Q? And so you start your equilibrium reaction, you throw a bunch of stuff in, and you set it up so when you plug in those concentrations, you get Q as 5. That means that you put too much what in the reaction vessel? Products. So if there's too much products currently in the reaction vessel, what direction does the reaction have to go to establish K? It has to go in the reverse, all right? So this is how we predict reaction direction, is you just plug in initial concentrations into your K expression, but it's not equilibrium, so we call it Q, and then we compare those two numbers. So here, if Q is greater than K, so that was this example, then the reverse reaction needs to happen in order to establish equilibrium. If it was the other direction, if Q was smaller than K, that means that there's too much reactants and the reaction needs to go forward to make K bigger. If Q does equal K, that means you're already at equilibrium. Okay, all right, so let's do some examples with pictures. Okay, so here's a reaction. A2 plus B2 gives us 2AB. There we go. And I gave you the K, I wrote it here. So there's the Kc expression for this reaction, AB squared over an A2 and a B2. And I'm going to just tell you that the Kc for this reaction is 1.5. all right? Okay, so it's 1.5. So let's predict with these different pictures which way the reaction needs to go to establish equilibrium. So the best way to do this is just count up the pieces that are currently present in the picture. So we're going to call these our initial conditions. Calculate Q and compare it to the K that's given. So this is kind of fun. All right, so ABs. So there's 1, 2, 3, 4, 5, 6 ABs in this picture. And then there's 1 each of A2 and B2. You agree with me? Yes. Okay, so let's just do all of these. In the second picture, we have 1, 2, 3 ABs. And then B's the blue ball. So B2, there's 2 of them. And A2 are the red balls, so there's 3 of them. I think that's right. Okay. And then the last picture, it looks like, oh, go away, calculator. There's 1, 2 ABs, and then there's 3 B2s and 2 A2s. Okay, great. So that just describes each of the pictures. So let's calculate Q, where we take these initial pictures and plug it into the K expression. So this is us calculating Q. So remember, it's AB squared. So we're going to square AB, all right? And then we'll just multiply A2 and B2 together in the denominator. So Q for this first picture is what? 36. Yes, so it's 36 over 1 because A2 and B2 are just, the concentration is 1. Q for the second picture is 3 squared, so 9. I'll just write it. 3 squared over 3 times 2, so 9 over 6, so 1.5. 1.5. And then the last picture, Q is equal to 2 squared over 2 times 6, so that's 4 over 6, so that is equal to 2/3, so 0.66. There we go. Okay, great. Yeah. Oh, there's 3. For which picture? The third one? Oh, there's 3 A's. Okay. It still doesn't change much. We'll see. Wait. 3 A2s, 3 B2s, so it's 3 times 3, so it's 4 over 9. Q is still a small number too. Okay, but thank you for correcting me. Yes, so Q in the third picture is about 0.5. It doesn't matter. It doesn't matter. It's still smaller than K. All right, so with these Qs, we can predict the direction each of these reactions will go. Is there any of the pictures are already at equilibrium? Yes, yes. So the second picture is already at equilibrium. So does that mean in this picture, does no reaction happen? Is no reaction happening? Are these balls just bouncing off one another? No. Yeah, that's the correct answer. Reactions are still happening. The forward reaction is just happening at the same rate as the reverse reaction. So like for every bond that you break, another one is made at the same time. So you don't see a net change in the concentrations of the balls. So again, being at equilibrium doesn't mean that the reaction stops. It just means the forward and the reverse are happening at the same rate. Okay, so what about this picture? When Q is 36, which direction does the reaction have to go? The reverse, yes, because I like to think, okay, Q is a big number, so I have too much products. I want to make Q become closer to 1.5, so I need to make more reactants. So in this picture, the reverse reaction has to occur. All right, so really what happens here is that the reverse rate becomes larger than the forward rate, and it's because of the rate laws. So the forward rate is just happening, at a larger velocity than the forward reaction. It doesn't mean that the reverse reaction stops because this is chemical equilibrium. It's just a smaller value then. And then our third picture here, because Q is smaller than K, Q is smaller than K, it's the forward reaction has to happen in order to get that Q back up to 1.5. So we need to produce more products in that case. And again, I like to just think, I don't like to memorize this. Like, oh, if Q is bigger than K, then it has to go in the reverse reaction. I like to think, oh, it's always products over reactants. If Q is big, it means that there's too much products, so I need to make more reactants. The reverse reaction has to happen. Or if Q is too small than K, then I have to basically take some of those reactants and make more products to make Q bigger. So that's how I memorize it, using concepts versus just memorizing like these 3 lines. I don't have room in my brain for that. Okay, how do we feel about that? Good. So I like to call this the quick and dirty way to determine which direction the reaction has to go. Q doesn't really mean anything, all right, because a reaction will never stay at those Q conditions. They will always go to K equilibrium. So basically calculating Q just allows you to determine, are we at equilibrium or not? And it'll tell you which direction we need to go if it's not super obvious. Okay, so there we go. Now we know what direction we have to go to. All right, so this is question type 2. All right, for ice tables, it's harder. It oftentimes requires a quadratic formula. But I'll teach you some tricks so we don't have to do it because I'm lazy. All right, we give you the quadratic formula on the exam if you want to do it. But I'm going to teach you ways where you don't have to do it. Okay. So here's the second type of question. So it's not the Sudoku method. I call this the quadratic formula method. It's where you're given initial concentrations and K, and you need to figure out the equilibrium line. But the process is still the same, where we need to fill in our ice tables and figure out, okay, what do we know? What do we not know? All right, so here are the initial concentrations. There is Kc. Calculate equilibrium concentrations of all the species. So let's just write our equilibrium expression real quick here. All right, so Kc is a small number, products over reactants. So A times C2 over AC2 is our Kc expression. So we need equilibrium concentrations in here to figure out what our equilibrium concentrations are, all right, or to figure out Kc. So if we plug in the given values that are given in this question, so AC2, so note how I put these I subscripts here to indicate initial concentrations. Are we okay back there? Okay, all right. So I'm just going to plug those in. So 0.05. 0.01, 0.01, all in molarity. Okay, so crap. We have reactants and products. Do you know which direction the reaction has to go? It's not super obvious, right? Like the forward could happen, the reverse could happen. So what do we have to do? We have to Q. Yes, we got to calculate Q to figure out which direction the reaction has to go to get to K. So let's just do a quick and dirty calculation here. So 0.5 over 0.1 squared is equal to 0.02. So that is my Q. So let's compare that Q, to K. So I like to think, do I have too much reactants or do I have too much products? I have too much products because Q is bigger than K. All right, so the reaction has to go in what direction? Reverse. So if the reaction's going into the reverse direction, then the products are going to have a minus X. So under A, it's going to be minus X. Did I do something wrong? Yeah. What? Would it? Oh, it would be, yes. Sorry. 0.1 squared over 0.5. I think the number is still right because I looked at my key. Sorry about that. Okay, so sorry about that. Remember, yes, products over reactants, just put the initial concentrations. Okay, so moving on. the reaction has to go in the reverse, so it's minus X on the product side. And so then we get a plus X on the reactant side. Right? That is in agreement with the reaction going in the reverse direction. We would not have known that unless we calculated Q. All right, and then we fill in the ice table just like normal. All right, so at equilibrium, AC2 will have a concentration of 0.5 plus X. A is going to have a concentration of 0.1 minus X. C2 will have a concentration of 0.1 minus X. All right. What's the trick with chemical equilibrium and ice tables? The equilibrium line always goes into K. Yes, so we have our equilibrium line. Let's put those expressions into our overall K expression. So K is equal to the two products over the reactants. So it looks like I have 0.1 minus X is A. We have the same expression for C2, so I'm just going to square it because I'm lazy. All right. And then on the bottom, we have 0.5 plus X. And because in this question, I give you K, this is equal to 0.001. Great. Can we solve X for X? Can we solve this expression? Yeah, there's one variable, one equation, yeah. This requires the quadratic, right? So I honestly don't want to do it, okay? So I'm going to teach you a trick that's going to help you on homework and life. So we need to solve this. This requires the quadratic. Anyone ever use Wolfram Alpha? Okay, I'm going to show you it. It got me through college. Because I'm going to just plug this into Wolfram Alpha and it will spit out what X is for me. I don't have to put it into A, B, C form, right? So I'm just going to teach you how to do that. All right, so there's my expression. So keep that handy. I'm going to use Wolfram Alpha and have it solve it for me. So there we go. All right, so Wolfram Alpha is a very intelligent engine, all right? And so what I do is I plug in exactly the expression written. I don't have to multiply, that 2 exponent across and get it into ABC form. I don't have to do that. I can just plug it in exactly as I have written on the other side. How can I do split screen? Can I do split? I don't know how to do it. What? Oh, it's the 3 dots. Okay, hold on, go away, calculator. 3 dots, split view. Boop. Okay, all right, so let's plug that in, that expression. So this expression. So 0.001 equals, so just be really careful with your parentheses. So parenthesis, 0.1 minus X. Oh, that's wrong. That's the wrong bracket. Dang it, no. Wolfram Alpha. Remember, computers are only as smart as the people putting in numbers. Oh my gosh. Okay, 0.1 minus X, parenthesis. Okay. Caret, where's my caret? Dang it. Oh, there it is. Caret 2 divided by, wrong one, divided by 0.5 plus, where's my X? X. Okay. Is that right? Is that right? Okay. All right. And then you just hit go. Do it, Wolfram Alpha. There you go. There are my solutions. Oh, but crap, it's the quadratic, so I get 2 solutions. So are both of them the right answer? No, only one of them is valid, but which one? You got to check, all right? So if you look at our work here, right, usually it's the subtraction ones. Only one of those X's can work. So look at these guys over here, all right? So see how it's 0.1 minus X? So can the 0.125, is that X our answer? No, it cannot be, so it has to be the other one. So using the quadratic formula, although I didn't actually do it, but that's okay. Using the quadratic, we get that x equals 0.076. And so with that x, what do we do next? Is that my answer? No, you have to put that x back in the equilibrium line, calculate all of the equilibrium concentrations. Is that my answer then? Yes, then that is my answer. All right? Ew, gross. That's disgusting. I don't want to do that. The quadratic formula, that'll take you way too much time on the exam. So I'm going to teach you a trick here, right, where we use our chemical intuition. So let me go back here. Okay, so it's here, all right? Note about the quadratic formula. We will actually never put a question on the exam where you have to use the quadratic formula. You can always use an approximation, but you need to know what approximation you can make. So the problem here, why we need to have the quadratic formula, is because we have an x term in the numerator and the denominator. That's the problem. Once it gets like that, it's harder to solve. So this expression, right, that's our k expression that we just did, that this requires the quadratic formula because we have x squared on the top and x on the bottom here. Wolfram alpha gave us these two solutions. I don't know, in your slides, I had the wrong numbers, but these were the two solutions we just got. All right, so this is the approximation we're going to make. K is small. Yes? So what is mostly present at equilibrium? Reactants. Yeah, so let's go back to this. Okay, so if reactants are, mostly reactants are present, right? If mostly reactants are present, then this x term that's getting added on is going to be quite small. Or here, actually another way to think of it. Reactants are mostly present, then the amount of, hold on, let me think about this. What am I trying to say? What am I trying to say? Yes, okay, so K is quite small. So the reaction stays primarily on the reactant side. There's already a lot of reactants present, all right? There's 5 times as much reactants as products. So this X term on the bottom of this reaction is relatively a small number. 0.5 is a pretty big number. Let's think about it, like 0.076, is just a small fraction of that 0.5 number of the concentration of reactants on the bottom denominator here. So when we actually put in that X value, the value for the denominator doesn't change that much. It only changes a small percentage. So the approximation that we oftentimes use to avoid using the quadratic formula is to ignore that bottom X, that bottom plus X, or sometimes it's a minus X. It's no big deal. Where that X is relatively small, oftentimes we need to inspect the magnitude of K to see if we can do it. And so if you ignore that bottom X, then the expression turns into this. Do you need to use the quadratic formula to solve this expression? No, you don't. All you have to do is multiply both sides by 0.5, take the square root of both sides, and then add x or whatever, solve for x. So this does not require the quadratic formula. So let's just see it. This is how I like to check it in Wolfram alpha, if we have to use the approximation or not. And again, it's oftentimes the it is the, where's my thing? Denominator that gets that plus, or minus x removed there. So what I oftentimes do is I do it in the quadratic form like this way on Wolfram alpha, and then I do it again where I just delete that plus x at the end. Oops. And then solve for it again. So if you solve for it again and look at the answers, are these answers too different than the ones we originally got? Are they that different? No, they're not. They're not super different. So that's when the approximation works, is when your approximation answers you get are similar enough. Usually it's within 3 to 5% of the answers you would have gotten with the quadratic formula. So I like these answers as well, all right? And so Yeah, these are the answers you get when you do the approximation that does not require the quadratic formula. But I already had it in Wolfram Alpha, so I had it solve it for me instead. So yeah, so let's actually go back and solve the this question. So with the quadratic formula, you get that x is equal to 0.076, but with the approximation, you get that the value of x is 0.077. So on an exam, those two numbers in your calculation aren't going to make a difference, especially if it's numerical, because we always put a certain percentage tolerance on it. Or when you go in and do the calculation, if it's multiple choice, it's just the last significant figure that's going to be different, all right? And so you'll be able to get your answer close enough to the answer as long as you use a valid approximation. So which one do you want to do, quadratic or approximation? Because we didn't answer the question yet. Let's do the approximation. So is that my answer? Is 0.077 my final answer? No, what do I have to do? Plug it back in, yes. So I plug this x value back into the equilibrium line to get the equilibrium concentrations of everything. So at equilibrium, we're going to have, of our reactant, 0.577 molarity. A is going to equal, what is that, 0.0, what am I trying to do? Okay. 0.1 minus 0.077. 0.23, and then that's the same concentration as C2 as well. All right, and so a way to check yourself is plug those equilibrium concentrations back into the K expression, right? And then what number should you get? The K value that's given. So I'm going to do that real quick. So if you plug these values we got in back into K, you should get something like 0.023 squared over 0.577. And hopefully you get K. 0.23 squared over 0.577. Yes, and I got 9 times 10 to the negative 4, so that's basically 1 times 10 to the negative 3. Yes? Can you repeat the question? They never will. They never will. Yeah, so you want to use the only valid one. Yeah, okay, good. You'll be doing a lot of these, so you'll see. You'll see that one will be valid, one will not be. And actually, if you don't use the quadratic formula, look, even if you use the approximation, right, it's a square root. Usually we ignore the negative one. But even in this example, the 0.122 won't work here because you'll run out of your product. All right, are we going to do another one? All right, let's just do another one. Want to do another one? Okay. Okay, let's do another one. So, initial concentrations, there is K. So this is question type 2. Ice table, I give you K and initial concentrations. You need to quadratic your way out or not. So ice table, I'm going to plug in my initial concentrations. A, D is 0.1. A and D are 0 and 0. And then there's my Kc value. So I'm just going to go ahead and fill in my ice table. What direction does my reaction have to go? Forward. Do I have to calculate Q? No, you can just use your intuition. Also, I mean, you could calculate Q. What would it be? Just using your head. 0, yes, and 0 is less than that number. So the reaction has to go forward. So minus x plus x plus x. And so at equilibrium, we have 0.1 minus x of the reactant, and then x amount of each of the products. All right? Okay, what do we do next? What do we do next? We just look at the ice table. Yes. What's the trick with ice tables? The equilibrium line always goes into K. So let's put that equilibrium line into K. So K equals So it's products over reactants. I'm just going to skip that step. It's x squared over 0.1 minus x. Do you agree with me? Yes. Okay. Equals 3 times 10 to the negative 10. Okay. Ew, that's a quadratic. Do you want to solve the quadratic? You do? No, I don't. I don't. So we're going to use another approximation here. So the idea here is K is small. So what do we have in excess at equilibrium? What's present at equilibrium? Reactants. So if reactants are present at equilibrium, are we going to lose a lot of reactant in this process? No, X is going to be really small. Because right now, before the reaction happened, we only had reactants. But K is a really, really tiny number, so the reaction's only going to go forward a tiny, tiny bit. So X is going to be small. Did I do something wrong? What if I had 2 reactants? In terms of what? There's some tricks. There's only certain types of questions we can give you that you can use the approximation. All right, just trust me for now? Okay, yes, yes. So if you had 2 reactants and 1 product, sometimes we can give you the product. Yeah, yes. Okay, so, or just plug it into Wolfram Alpha if it's a homework question, because mastering won't know. All right, so the approximation I'm going to make here, all right, so you can solve this using the quadratic formula. Let's just do it. All right, let's just do it. Let's do the quadratic. Oh, where are my dots? All right. Okay, so filling in the quadratic. 3e negative 10 equals x squared. What comes next? Oh yeah, divided by 0.1 minus x. Are you going to start using Wolfram Alpha? Yes. Is anyone's mind blown? All right, equals. What does it spit out? Okay, only one of these numbers will work. Which one will work? The positive one. Very good. So the quadratic gives us a value. Okay, so quadratic x equals 5.47 times 10 to the negative 6. So is x a small number? Yeah, it's real small. All right, and so the reasoning behind our approximation will be valid. X is super small, so we can probably ignore it in the calculation. So let's check what that will look like as well, because I want to show you both methods to prove to you using the approximation works. So X is really small, so if we just ignore it on the denominator, think about it, okay? Think about it. If we actually put X back into this expression, all right, 0.1 minus this tiny, tiny, tiny number, are you changing that 0.1 drastically? You're not changing that number that much. So why don't we just make it easy for ourselves and just ignore that minus x part? So using the approximation instead, all right, where we ignore that minus x part. So I'm just going to do that right now. Come on, where's my keyboard? Where's my keyboard? Oh my gosh, where are you? Go, show keyboard. What? Okay, whatever. Minus, just 0.1. So I just removed that x part on the denominator. So if we look at the solutions, those are the solutions. Are they any different than when we use the quadratic formula? No, they're the same exact number because x is really, really small. But we were able to, we wouldn't have to do the quadratic here if you can use your intuition and think, okay, K is really small. The reaction is going to remain on the reactant side. So x is going to be, you're only going to make a tiny, tiny bit of products, just a tiny bit of products. So x is going to be really small. I can ignore it in the denominator because the initial concentration of that reactant is rather large. So it's not going to make a big difference. All right? And so using the approximation, where instead we just say x squared over 0.1 equals k, we get x is the exact same number, 5.47 times 10 to the negative 6. Is that my answer to the question? No, it's not. So we actually have to go through and calculate equilibrium concentrations. So X is the concentration of A and D, but then we need to plug that number back in to get the concentration of AD. But what you see, if you, in your calculator, you put 0.100 minus that number, you get 0.99999, right? And so it is essentially, at equilibrium, AD is essentially equal to 1.00 with, when you just round within sig figs. All right, so in this example, we just make a tiny, tiny bit of product because K is so small. Yeah. Mm-hmm. No, so when we calculate Q and we calculated 0, 0 is less than that tiny, tiny number. So the reaction has to go forward. So the rule is when Q equals K, that the reaction is at equilibrium. So 0 does not equal K. All right, so we do actually make a tiny, tiny bit. All right, so we never have to do the quadratic. All right. If you want to on homework, you can. Sometimes you do have to actually do the quadratic on homework. So I would always have a page of Wolfram Alpha up, but it's in good practice to check, okay, do it with the quadratic. Think about, what approximation can I make? Delete that part and see if you get a similar enough answer for X. Okay, we're going to do another one. Yay. Yay. All right, so let's fill it in. So these are pressures. It's fine. We're calculating Kp now. We're just using pressures in our ice table instead. So Kp equals, what is it? Oh, A times B over AB squared. Great. Ice. So pressure initial concentration of A2 is 0.5. B2 is 0.5, AB is 0. So which direction does the reaction have to go? Reverse. So it's minus X plus 2X. Don't forget the stoichiometry. Okay, let's add it up. So at equilibrium, AB is going to be 2X. And then A2 and B2 are going to be 0.5 minus X. For both of them, 0.5 minus X. There we go. Cool. What do we do next? We look at it with loving eyes. We just look at our ice table with loving eyes. No, we need to stick that equilibrium line into the K expression. So K equal, in this case, Kp, so pressures, whatever. Products over reactants, so 0.5 minus X, and then another one, so I'm just going to square it. Yes, okay, good. Square it. Over 2X. Is this the quadrat? Oh, sorry, 2X squared, sorry. Equals 100. Crap, so you might be looking at this and being like, oh, it's another quadratic. I need to put, distribute the X's and stuff. This one actually does not require a quadratic. There's a trick. There's a square in both the top and bottom. So I can actually just square root both sides. Yay, yay. And so if you square root both sides, then the square goes, the two squares go away. So it simplifies to 0.5 minus X over 2X equals 10. That doesn't require a quadratic. But, I mean, if you have Wolfram Alpha next door, you could plug it into and get the same answer. But we could, in fact, give you this one on an exam, because there is a way to simplify it that does not require the quadratic. Okay, so then we can actually solve for X. So, I'll do the math. I'll prove to you I actually do know how to do math. So 0.5 minus x equals 20x. Does that sound right? And then 0.5 equals 21x. So x equals 0.0238. Cool. Is that my answer? Nope, you got to plug it back into the equilibrium line. So that x goes back in there, and so we get at equilibrium AB is equal to 0.047-ish. What is this, ATM? And both AB and B2 have pressures of, okay, I can calculate that. 0.476 ATM. Both of those. Okay, once you plug the x back into the equilibrium line. All right, so in that example, we don't have to do the quadratic formula. Thank goodness. Okay, yes. Yeah. You're asking, can we use an approximation here? Let's see. Could we use an approximation here? Maybe. I don't know. Well, one, you don't have to because we can simplify it. I mean, the best way to think, if you ever have this question, if whether you can do the approximation, put the full expression into Wolfram alpha, let them solve it, then delete the part that you want to approximate to make it so you could solve it and see if the answer matches or is close enough. If it doesn't, then it means that you can't use the approximation. I'm not sure if you could do it here. K is fairly large, so it's going to stay primarily on the product side, but I don't know to what extent. I don't feel like putting it into Wolfram alpha, so that's a good practice for you to check if you could make that approximation. So what you're wanting to do is get rid of this x right here on the top. That's what you want to do. So I will just say most approximations that we make involve the denominator. Most, I would say all of them. So yeah. So I'm going to just go quickly back to this question where we made the approximation in the denominator. This is a very, very common approximation that we will make for the next 3 chapters, right? This work that I showed you right here, we will apply to weak acids and weak bases in chapter 16. All right, so do keep this in your back pocket. All right, okay. We'll use it a lot. But you don't have to use the quadratic, so it's not too bad. All right. All right, so there we go. There we go. I would suggest using Wolfram alpha for online homework so you can be lazy and not actually have to do it. Okay. All right, so we're going to move on now. All right, and we did a lot of predicting which way reactions will go given like initial conditions, but we can also predict directions reactions will go or chemical equilibrium will go when they're already at equilibrium and we stress the system. When we stress the system. Ways that we can stress the system, changing concentrations of reactants and products. So if we're already at equilibrium and we throw in more reactants, how does the equilibrium need to adjust to that change? Or we could remove concentration of reactants or products. Again, how does the equilibrium need to change? Keeping in your back pocket that K is just products over reactants will allow you to figure out, okay, which direction does it need to go to reestablish equilibrium. We're going to bring back to the idea of rate laws again and the fundamental idea of what chemical equilibrium is. It's when forward rate equals reverse rate. But once we start changing concentrations of things, we change the rate law a little bit. So there's a subtlety here of why reactions shift when we disturb the system. All right, there's what I call the quick and dirty way to figure out the direction chemical equilibrium have to shift, but there's also a nuanced conceptual thing we need to think about in terms of rate laws. All right, so okay, yeah, so when we stress the system, what happens? So the reaction quotient helps us predict what direction the reaction can go. If we change the system, we can quick calculate Q and figure out what direction it goes. What am I supposed to say here? Use the same so I forgot to fill in this blank, use the same equation as K, but the system concentrations are not at equilibrium. That is what our reaction quotient is, right? Those are our back of the envelope calculations just to figure out which direction the reaction needs to go. So Q can tell us a lot of things if we are given initial conditions, you know, changes in the forward and reverse reaction rates tells us which way we need to go to reestablish K, and comparing Q to K also helps us predict qualitatively the direction reactions need to shift when undergoing a stress. This is called Le Chatelier's principle. All right, there's a lab that you're going to do in lab, I think it's called LCP, Le Chatelier's principle, where you'll shift chemical equilibria and see, okay, how does the reaction respond to these changes? So when I talk about changes to the system, it can include adding or removing reactants, so changing concentration of species. We can also change pressure, and we can also change temperature of a reaction. Okay, so here are the three different ones: concentration, pressure, temperature. I like to think of this as like a seesaw, right? If you think of a chemical equilibrium as a seesaw that's like equal, right? And you add more reactants, so the seesaw looks like this. Okay, that's me stressing the seesaw, and I push down on one side. What do you, as the reaction, need to do to make it go back to being equal? I need to add more products on this side, so the reaction shifts in this direction, in the forward direction, to make the seesaw equal. So that's like qualitatively the quick and dirty way to predict which direction reactions need to go. So let's actually look at an example. Let's look at our Haber-Bosch process, the reaction to produce ammonia. All right. So let's say we have this equilibrium. It's at equilibrium already. We have a vessel of it. Okay, all three species are present. It's at equilibrium. Q equals K if you want to calculate Q. All right. So what would happen if we added nitrogen to the container? If we add nitrogen to the container, are we at equilibrium anymore? No. No, we're not. So what direction does the reaction have to go? Forward. Yes, we make more products. All right, if we increase the amount of nitrogen. What I like to think, it's like, okay, you push down on this side of the seesaw. In order to get it back to equilibrium, I need to go in the forward, put more weight in the forward direction to make it even again. All right, okay. Or you can think of it this way. So remember what K is. K is equal to, in this case, ammonia squared over nitrogen to the 1 over H2 to the 3. If I add more nitrogen, a bigger number is in the denominator. I'm putting a bigger number in the denominator. Q is going to be smaller. It's going to get smaller. All right. And in order to get back up, to get Q back up to K to reestablish equilibrium, I need to make more product in that case to make that number bigger. So that's another way to think about it too. K and Q can help. All right. What if we decrease the amount of hydrogen present? Which way does the reaction have to go? Reverse, yes. So a way to think about that is, okay, I remove some hydrogen, I lift that side of the seesaw, so the reaction needs to go in the reverse in order to fill that void. Yeah? Okay. All right, what if we neutralize some ammonia with an acid? Yes, in forward. It's just like saying we're basically saying NH3 decreases in concentration because we're neutralizing some of it, converting it into something else. So if we neutralize some ammonia, the equilibrium will try to reestablish itself by filling that void that we created. It'll go to the forward direction. All right, what if we increase the pressure of the reaction vessel by squeezing the volume of the container? This forward, you said that so quickly. Yes, it is the forward direction, all right? Because if we increase the pressure of this vessel, all right, increasing the pressures of everything increases. The chemical equilibrium does not like that when it increases pressure, so it's going to try to relieve some of the pressure in the system by moving to the side of the reaction with less moles of gas. So if you look at here, this reaction, how many moles of gas are on the reactant side? 4, but there's only 2 on the product side. So if I increase the pressure of the whole reaction vessel, the reaction will move into the direction where there's less moles of gas, and doing so will relieve that pressure that you stressed on the system. Okay. All right. What if the volume of the container is doubled? Backwards, yeah, so it's the reverse of that. So if the volume of the container doubles, pressure actually decreases overall. And so again, the chemical equilibrium doesn't like being disturbed, so it's going to replace some of that pressure by moving in the direction where there's more moles of gas to fill that void. So it's going to go this way. All right, adding an inert gas to the container. This one's kind of tricky, so nothing actually changes. Okay, so if we add an inert gas to the container, the total pressure of the container increases, but the partial pressures of things, N2, partial pressure of nitrogen, hydrogen, and NH3 do not change because we're just adding an inert gas. All right, so it's not involved in the chemical reaction. P total changes, but the partial pressures don't change. And so remember, it's the partial pressures that go into our K expression, so they don't change. All right, so 6 is kind of a trick question. All right, so what if we heat the reaction vessel? This one's less obvious. There's a little small detail that I kind of glossed over. I have the chemical reaction, but what else do I tell you about this chemical reaction? It's exothermic. So this is the quick and dirty way to determine what direction it goes into. You guys are real good in saying, oh, if I add more product, the reaction goes in the reverse reaction. If I add more reactant, it goes in the forward reaction. So let's just treat heat as a product or reactant. So if this is exothermic, is heat a product or a reactant? What? Reactant? When so in a combustion reaction, right? When I blow up my hydrogen balloon, that's an exothermic reaction, right? So heat, what are you're seeing heat. Heat is being released, so it's the product that we're seeing. Heat in an exothermic reaction is a product. Product, yes, yes. We like that. We like when heat is a product, all right? Okay, so the quick and dirty way is just to treat heat as a reactant or product. So when we heat the vessel, we're adding what? A product. So which way does the reaction go? In the reverse. Yes, that's it. And I think there was like a post or pre-lab question about that. Yeah. About like solubility. Do you remember that? Yes. Okay, and then let's do this one. When the reaction is cooled, you're removing the product now. So which way does the reaction go? Forward, yes. Okay, so yeah, the one pre-lab or post-lab question, it was like, okay, you have an exothermic dissolution process. All right, so you have like a saturated solution and it's exothermic, so heat is a product, right? And it asked, how does solubility change when you heat the solution? And so what you do is, okay, if you heat the solution, you're changing the dynamic equilibrium of a saturated solution, right? When you heat the saturated solution, you're adding a product. So which way does the reaction go? In the reverse. So if you produce more solid, that means not as much stuff is going into solution. So does solubility increase or decrease when you add heat in this example? It decreases because you can't hold as much dissolve as much solid anymore. You're pushing it towards the solid phase. That more stuff is going to come crashing out the bottom of your beaker. So that's the quick and dirty way. There's actually a more nuanced way of the real way to predict temperature changes. Okay, so that's the basics of Le Chatelier's principle, but we're going to go into much more detail of the concepts here, all right? Like, yeah, we add more reactant, the forward reaction goes forward. But why? It's due to the idea of chemical equilibrium is when the forward rate equals the reverse rate. Those rates have rate laws, unfortunately, all right? So forward rate, so here, the forward rate, okay. I just want to show something. So forward rate equals reverse rate. So here's the same chemical reaction, right? We have N2 plus 3 H2s give us 2 NH3s. Okay, so when we're at chemical equilibrium, the forward rate equals the reverse rate. If we add hydrogen gas, so remember our first example, we add hydrogen gas to the equilibrium, we disrupt the equilibrium, the reaction will go in the forward direction in order to reestablish equilibrium. So if we think about this, all right, so I'm just going to zoom in here real quick. If we increase the concentration of H2 that's initially at equilibrium, what rate do we change at that moment? Which one do we change? The forward one. So if we're changing the concentration of H2, increasing it, this number in the rate law for the forward reaction changes. So what happens the instant we put H2 into something that's currently at equilibrium, we disrupt this, this process, and the forward rate is now greater than the reverse rate at that moment until it reestablishes equilibrium again. We don't change anything about the reverse reaction because we're actually not changing anything about the rate law for the reverse reaction. So there's a small detail. And that's what this picture is trying to say. Okay, so we have a system initially at equilibrium. So that's what these three lines are saying. The concentration of those things aren't changing with time because it's at equilibrium. But at a certain moment, we add hydrogen gas. We add just like a puff of hydrogen gas. What happens? Our intuition knows that the reaction needs to go in the forward direction. All right, and so what happens is that we consume some of that hydrogen gas that we placed in it. All right, it gets consumed, so that's why the concentration goes down. But at the same time, the concentration of product, NH3, goes up because we're going in the forward direction. We're consuming some of that hydrogen and producing some NH3 to reestablish K. But remember, stoichiometry, if we add H2 and the reaction goes forward, we also consume some N2 at the same time. So what we see is with time, the moment we add hydrogen gas, some of that N2 is also consumed at the same time. All right, until we reestablish equilibrium again, like, past this point. And so those are the details here. So I think I already asked this. How does the forward and reverse rates change when hydrogen gas is added? And again, if we look back at the basis, the concept of what chemical equilibrium is, we're only adding hydrogen gas to this sample or to this system. So what happens is that just the forward rate at that instance is greater than the reverse rate, just at this point in time, until we reestablish equilibrium again. All right. Here, okay. How does Q change the moment H2? Oh, I didn't answer this one. How does Q change when we add H2? It gets smaller because we add H2, which is a reactant. So there's a bigger number in the denominator. So Q is smaller than K at that moment. So Le Chatelier's principle does agree with everything that we're talking about here. All right. And so what's this last question? Why has the N2 concentration decreased once equilibrium is reestablished and relative to the initial concentration? And the answer here is not because K is changing, but it's because hydrogen concentration increased, so that means N2 needs to be consumed in order for the reaction to go forward. So that's why the concentration of N2 goes down with time, because some of it's consumed in order to reestablish equilibrium. Okay, so 3 minutes, I can do the next one. So let's do a different one. Let's suppose some NH3 is added to this system at equilibrium. What does our intuition say? When we add NH3, what direction does the reaction go? Goes in the reverse reaction. So we want to draw the graph that shows that. That's the hard part. All right? So the reverse reaction is happening here. So if the reverse reaction is happening with time, what direction does the concentration of NH3 go? It's going to go down, yes. But is it going to go down lower than what it was? No, it's going to go down, but it's still going to be higher than what it was. All right, so that's NH3. Then what happens to hydrogen and nitrogen? They go up. Yes, because we're going in the reverse reaction. We're reverse direction. We're making more reactants here. So hydrogen concentration will go up with time, and then nitrogen concentration will go up with time. There we go. Okay, and there's our new equilibrium. So once equilibrium is reestablished, hydrogen concentration is what? Higher or lower than it was initially? Higher, yes, because we added more stuff to the reaction vessel. The reaction went in the reverse. NH3 is higher or lower than it was initially? It is also higher, yes. Even though it went down with time, right? We added more product. It went down with time. It's not going to go down lower than it was initially. And then N2 is what? Higher or lower than it was initially? Higher. Okay, great. Perfect. And so last question here. The rate of the forward reaction, if we compare the rate of the forward and the rate of the reverse reaction at this moment where we added NH3, what is greater at that moment? The reverse reaction, yes. It is the reverse reaction, yes. Okay. All right, so we'll pick up here. Oh, no, we'll do midterm 1 review on Tuesday. So, yeah.